One of the critical parts of switch mode power supply measurements is assessing the noise they're generating. This seemingly simple task can be done in multiple ways and with multiple results. Hello and welcome back. Today I want to look at some of the probing techniques that are used when measuring the noise and ripple of a power supply. First, we will look at what these parameters are and why we care about them, and afterwards, test things out. So if you're curious, then keep watching. First thing to understand is what the actual waveform is telling us and why. In general, both the input and output of a converter will be at a defined average DC voltage, but also have some amount of perturbations imposed over it. There are three main causes why the DC level isn't really a DC. So first, a switching converter usually contains a switch, which switches, and while both the input and the output is connected to something, most of the energy going through the switch is not directly pulled through the lines, which have some amount of inductance and resistance, but rather the energy is transferred from the local decoupling capacitors. So the first element in our measurement is a triangular shape. This is typical to an ideal capacitor being charged and discharged. Now, if we consider that the capacitor is not ideal, it will also have some ESR. Based on the magnitude of this resistance and the current passing through the capacitor, you will also see these jumps appearing in the waveform. Finally, the capacitor, as well as every other interconnection in the circuit, has inductance, and this will lead to various ringings and extra noise. This is mainly happening during the exact moment when the switches are switching. So the final waveform to expect is quite a messy thing with multiple components and causes. The relatively low frequency component is called the ripple, while the high frequency bit is the noise. So based on your application, you might want to just measure the ripple or the ripple and the noise. Okay, so you have ripple and you have noise. But which one should you be measuring? Well, it depends on why you're performing the measurement in the first place. What is the reason for checking this? Well, there are two main ways in which ripple and noise affect the performance of an electronic circuit. So let's have a look at these. So the typical environment in which you find the switch mode power supply, which has noise and ripple both on the input and output, is on the one hand connected to some sort of supply, a battery, another supply, or something else, and at the other end there is a load. Now, the supply usually does not care that the switch mode power supply is noisy. It's usually low output impedance, so very little noise and ripple actually gets there, and at the other end, the load usually has some sort of local decoupling capacitor, so most of the noise is filtered out, and you only end up seeing the ripple. Here we care about the ripple amplitude, since that could make the load unstable. Finally, the noise, while it doesn't normally reach the supply or the load, will still be either conducted or radiated to nearby circuits or the environment, causing other issues. It's therefore critical to differentiate between noise and ripple, since each of these has a different reason to be measured. You might have strict emission requirements, and then you want to minimize the noise, both on the input and the output, or you might have strict load supply requirements, and then you have to minimize the ripple at the output. Usually, input side ripple is not all that critical, unless there is another load supplied from the same rail, which has some more critical parameters. Whether it's the noise or the ripple that you're interested in will usually be application dependent. But the next problem to address is how do you actually measure it in an accurate way, especially when you're talking about relatively small signals. So today I will be testing out a few methods and tools. The measurement equipment of choice will of course be the oscilloscope, but connecting this to the circuit is where things get complicated. While you do have your standard probes in either X10 or X1 configuration, so some probes have the switch, but another common way is to use 50 ohm based setups. While I guess you could buy these, it's easier to just homebrew them. Each of these can be used to perform measurements, but the exact choice will be impacted by what exactly you wish to measure. To evaluate the various setups, let's analyze these circuits in the simulator. So here, as a reference, I created a waveform similar to what we can expect to be measuring. So I used a current source to charge and discharge a capacitor, and then also added in the series resistance and series inductance. To stabilize the circuit, there's also a resistor in parallel with the current source. So if we simulate this, the outcome is a triangular shape with jumps and spikes characteristic to what a power supply input or output will present. So we get both our ripple and our noise. Now, you could of course simulate a complete power supply, but then the simulation would just take too long. Using this simplified model will help with keeping the simulation times more reasonable. Anyway, the other critical element in our analysis is the oscilloscope. So for the final setups, I took a behavioral voltage source that just takes the voltage from our signal generator and then applied it to the standard impedance of a typical oscilloscope. So most oscilloscopes set to high impedance input will have a 1 megohm in parallel with about 10 to 15 picofarads of capacitance. And well, with a direct connection, we get to read exactly what we're supposed to read. So the two waveforms, the signal generator and what the reference is measuring, are identical. But such a direct connection is not really realistic. So now we need to provide a realistic way to interconnect the two. And for this, we have two options. An oscilloscope probe set to extend mode or set to X1 mode. In extend mode, we have the probe tip, a 9 megohm resistor, in parallel with some amount of capacitance, and then a piece of lossy transmission line, for which I provided the definition above. When the probe is set to X1 mode, we simply short over the probe tip and leave the line in place. Now, if we check out the response of these two circuits, we can make a few observations. So first off, the extend mode of the probe preserves the complete signal. We can see both the ripple as well as the noise spikes. And these are more or less identical to the reference. Any difference in the simulation will be coming from the probe model that I used. But in real life, the probe should not affect the shape of the signal. What it will affect, however, is the amplitude. The extend in the probe's name means that the signal is attenuated 10 times. So while the reference is about 4 volts peak to peak, the signal on the extend probe is about 400 millivolts peak to peak. On the other hand, if we look at the X1 probe and compare this to the reference, so by overlapping the two, we can make two important observations. The exact ripple value is unattenuated. X1 simply means divide by 1, so it's the same value, but the noise is greatly reduced. So it's nowhere near the reference. So the X1 probe will preserve the low frequency content of the waveform, but not the high frequency content. If you check the leaflet that comes with a probe, you will observe that the rated bandwidth is different for X1 and extend modes. The extend mode provides the rated bandwidth of the probe, whereas the X1 setting limits this to, in this case, 20 MHz, but it could be lower. So the observed behavior in the simulation is perfectly normal. Now, when the intention is to measure ripple only, usually you will want to eliminate the high frequency noise. So the first important setting on the oscilloscope is the bandwidth set to 20 MHz. This is a common standard present on most devices. The other thing to remember is that since we're measuring very small values, you either need to set AC coupling or you can keep DC coupling if you set an appropriate amount of offset. DC coupling will be better to preserve the low frequency phenomena, but AC coupling just makes life more easy. Anyway, if we now measure a real supply with these settings, using an appropriate low noise connection, and the probe set to extend, we get this waveform, and if we use another probe as well, set to X1 and measure the exact same thing, we can start to compare and see the difference. Well, if we look more closely into the results, the yellow trace is the extend probe, and the blue is the X1 probe. While there are a couple millivolts of difference in the peak-to-peak value, mainly this is because of the noise peaks. This difference is not really problematic, since if we overlap the traces, we are getting more or less the exact same ripple. The important aspect to observe, however, is that the yellow trace is more noisy all around, not just during switching, whereas the blue trace is far cleaner. The reason for this is that while the roughly 10 mV blue trace is generated from a 10 mV signal present at the oscilloscope's terminals, the yellow trace has a source 10 times smaller, about 1 mV of signal. The measurement device is not ideal, it's noisy, so the same noise is added in both signals. But in one case, it's far more visible than in the other because of the smaller signal-to-noise ratio. So if your intention is to measure only the ripple using a standard voltage probe, you will first need to set the bandwidth limit to 20 MHz, and setting the probe to X1 mode will increase the signal amplitude tenfold, making it far cleaner and easier to measure. Now, using the standard probe, you can make both ripple only or ripple and noise measurements, but there are a few limitations. The probe is relatively large. If you want to make measurements while your test circuit is fully assembled, it can get quite problematic. The probe also has a limited operating temperature, usually smaller than the circuit that you're measuring, and as we've just discussed now, measuring the noise is only possible with a factor 10 attenuation, making small signals difficult to observe. So another important way of performing measurements is using a piece of coax cable. So if we come back to the simulator and just place a piece of 50 ohm transmission line in between our signal source and the oscilloscope model, and we run this, we can observe that at the output, we are seeing a huge amount of unwanted things appearing. So let's just overlap this with the reference and just zoom in a bit. So while the low frequency content is sort of unaffected, the high frequency noise is completely distorted. So while we do not have any attenuation, we don't have a clean measurement method either. So the easy way to fix this is to create a matched impedance system. This means having a 50 ohm signal source. This can be done by adding in a 50 ohm resistor with our signal source. Then this is matched to the 50 ohm transmission line. And we also need 50 ohms at the other end. So for example, if the oscilloscope has a built-in 50 ohm termination. With this setup, we have a perfectly preserved signal, but if we compare this to the reference, we can see it's smaller. To be more exact, it's half. If we multiply it by 2, then we can see it perfectly matches our reference. Now, if we apply the same principle to our 1 megaohm oscilloscope, so in case the oscilloscope does not have a built-in termination, and you just add in the 50 ohms externally, we can see that we get more or less the same behavior, but the high frequency noise is a bit attenuated. So the series resistance that we've placed and the parallel oscilloscope's capacitance is forming a low-pass filter. So therefore, the bandwidth of this setup is limited. With my particular scope's parameters, this should yield a corner frequency of around 212 MHz, which is just slightly above the device's built-in bandwidth limit. Therefore, this should not present any major limitations. But anyway, final thing to mention is that while this sort of setup works, as it stands, you're still introducing a 100 ohms in parallel with the circuit. So this will draw quite a bit of DC current in case you're probing higher voltages. Now, in case you just want to observe the AC ripple and noise, you can of course add a capacitor in series and eliminate the DC component. This sort of a setup should however be done with care, since if the capacitor is too small, then the signal again will be distorted. So here, our switching frequency is about 100 kHz, and with the blue probe, the one with the 100 nanofarad capacitor, we are getting a bulging of our trace. So it's not a straight line as it's supposed to be. So at this test frequency, we should be using a larger capacitor to get an accurate reading. To test this out, I built a rather crude looking probe tip. It's a bit of scrap PCB with a SMA connector at one end, a 50 ohm resistor and a 1 microfarad capacitor in series, and then a set of needle test probes. This is connected through some 50 ohm coax to an inline termination and then to the oscilloscope. So my device does not have a built-in 50 ohm option, but if you don't have the inline termination either, you can always use a T-junction with a termination placed onto it. It's not as good, but in most cases, it will do. Anyway, I set up the same test as before, and I will be measuring the power supply with the X10 probe and with this thing at the same time, just to see how they compare. Of course, the bandwidth is set to maximum to properly observe the noise. So again, the yellow trace is the standard X10 probe, and this time the green trace is the X2 50 ohm probe. Peak-to-peak values are similar, the yellow trace being a bit larger, but as before, if we overlap the two traces, these are the same. It's just that the yellow is a bit more noisy. Next, just to confirm that both probes are measuring the same noise, let's just zoom in into the switching transitions. And here we can see that both probes are measuring more or less the same thing. The various deviations can be attributed to the noise which is present in the X10 probe. While this approach works quite well, it still presents the issue that it attenuates the measured signal by a factor of 2. It's still better than attenuation by 10, but in the interest of having the best possible signal-to-noise ratio on a passive probe, is there a way to create a high bandwidth X1 probe? Well, with a bit of care, there is. Now, the main reason for which we used 50 ohms at both ends of our X2 probe was to reduce reflections and have a good signal delivery system. But is this really needed? So let's remove one resistor at a time and check the results. So in the case where we only have the parallel resistor, the low frequency content seems to be unaffected, but the high frequency bit does present quite a bit of ringing. The main issue here is that our 50 ohm transmission line does not terminate into a 50 ohm load, but rather 50 ohms in parallel with 15 picofarads. If the termination would be ideal, only 50 ohms like with an oscilloscope with a proper termination, then this issue would not appear. But as it stands, part of the signal arriving at the oscilloscope gets reflected, and then reflected back again at the other end, leading to this oscillation appearing. On the other hand, when we check the series resistor setup, we are getting a much cleaner waveform. So both the low frequency bit as well as the high frequency bit are much nicer. So even though we are getting a reflection on the oscilloscope side, when the wave arrives at the other end, it sees something much closer to an ideal 50 ohms. So all of the reflection gets absorbed. Now, in general, both of these methods, either series or parallel resistors, should produce an X1 waveform, but the accuracy of the measurement will be highly dependent on the amount of imperfections and the exact values that are used. To test this out, I performed two measurements, one in which I used the probe tip highlighted earlier and connected directly to the oscilloscope, and in the second set of measurements, I placed the inline termination at the oscilloscope side and just connected the 50 ohm transmission line through a capacitor to the test circuit. I used the same probe as before, just placed a short circuit over the 50 ohm resistor. In both cases, I also used the normal X10 probe to have a direct comparison of results. So first off, we have a similar setup as before. In yellow, we have the X10 probe, and the green is the 50 ohm X1 probe. Here, we are looking at the measurement in which the resistor was in series. So both measurements look similar, and by overlapping, we get a clear correlation. The peak-to-peak value is again smaller for the 50 ohm probe, but just like before, this is also less noisy. If we zoom into the various spikes, we can observe that these are a bit cleaner on the green trace, but still look a bit attenuated. Now, moving on to the parallel resistor setup, we are getting a very similar set of results. Both the low and high frequency bits seem more or less the same. And when zooming in, we don't really see the oscillations that we've observed in the simulator. Maybe just a bit of hump in this area, but nothing really significant. So either the amount of discontinuities is much smaller, or the real transmission line just attenuates them. But all in all, both the series as well as the parallel resistor X1 probes seems to give more or less the same results. In the end, while using homemade X1 or X2 50 ohm probes is a legitimate way of probing, this will mainly work when observing low impedance circuits like power supplies inputs and outputs, and will mainly be worth it when observing very small signals. The attenuation might not be exactly 1 or 2, deviations will occur based on the used components, as well as the signal source impedance, adding a bit of error into the measurement, but even so, if you're on a tight budget, this will still produce useful results. And with that said, hope you enjoyed this video, and if so, there are more similar videos on my channel that you might want to check out. And if you want to be up to date with my latest releases, also consider subscribing. See you next time. Bye bye.